Math 1332, Chapter 10, Probability and Counting Techniques. Section 4, Tree Diagrams, Tables, and Sample Spaces. Video 4, Calculating Probabilities Using Tables, Pair of Dice. Many games, such as board games and casino games, involve rolling a standard pair of dice. Each die is a cube with the numbers 1 through 6 on each face. A single fair die has a probability of 1/6 for each number. Calculating probabilities for rolling 2 dice isn't difficult, but it helps if we have a table representing the sample space. Now, for the students in my class, I am going to make this table available for you in Canvas, and it looks a little something like this. It's basically a 6x6 addition table, where we have the first die represented on the top for each column, 1 through 6. And the second die represented on the left with each row 1 through 6. And in each cell, we have the ordered pair, the first die, comma, the second die, and the sum. So for example, if we look right here at this one, this means we rolled a 3 on the first die, which I color-coded for red for your convenience, a 4 on the second die, which I color-coded blue for your convenience, for a total of 7. So as we do some probability problems involving rolling 2 dice, you need to keep in mind that the first die is in red, the second die is in blue, and the sum is after the ordered pairs. Let's take a look at some questions. Calculate the following probabilities for rolling 2 dice. Well, for all of these, we're going to have the same denominator. Because remember, in theoretical probability, the denominator is the cardinality of the sample space. Translation, it's the number of ways you can roll a pair of dice. If we go back and look at our sample space of rolling 2 dice, you'll notice that there are 6 columns indicated by the fact that the first die can come up 1 through 6. And there are 6 rows indicated by this fact that the second die can come up 1 through 6. So this is a 6x6 table. 6 times 6 is 36. Or you could count each individual pair, and at the end you would see that there's 36 of them. That means that the cardinality of the sample size is 36, which means in every single probability that we're about to calculate, our denominator will be 36. So let's go ahead and get those set up. I'll pause the video and do it. Okay, now we just have to find the number of outcomes in the sample space and the 36 ways the pair of dice can be rolled that satisfy each event. Starting with A, a sum of 9. Okay, let's go to the table and let's find all of the sums that equal to 9. The first one that I see is in the third row where the second die is 3 in the 6th column. 6 plus 3 is 9. The next one I see is diagonal below and to the left of it. 5 plus 4 is 9. Continuing the pattern, 4 and 5 is 9. 3 and 6 is 9. These are the only 4 cells in the table where the sum is 9. These are the only 4 outcomes in the sample space that satisfy the event. That means that the probability of rolling a sum of 9 is 4 out of 36. Now, it is worth warning you that 36 is very composite, very reducible. It's reducible by 2, 3, 4, 6, 9, 12, 18, and of course 36. So chances are a lot of these probabilities are going to be reducible. I can reduce 4 over 36 by 4. 4 divided by 4 is 1. 36 divided by 4 is 9. So the first probability is 1/9. I'm going to insert some partition lines because these numbers are all going to run together. All right, that's a little more organized and easy to read. You may have noticed between the beginning and the before I pause and after that the words jumped up or down just a little bit. I had to reposition the text box just slightly. But now we can calculate all of our probabilities without the numbers running into each other. Hooray. All right, part B, the sum is 6 or 12. Well, pretty much the same song and dance as before. We just have to go back to our sample space get rid of what we saw before, and now find all the sums that are 6 or 12. 1, 2, 3, 4, 5. Those are all the 6s. 6, that's the only 12. There's a total of 6 outcomes in the sample space that satisfy the event. A total of 6 outcomes that have a sum of 6 or 12, which means this probability in part B is 6 out of 36, which can reduce by 6 to give 1/6. So far, so good. I invite you to pause the video and try to figure out the rest of these. The PDF for the sample space should be in the module just before this video. All right, the sum is greater than 9. Well, same thing as before. Now we just got to find all the sums that are greater than 9. Let's get rid of these. If the sum is greater than 9, that means it's 10, 11, or 12. 10. It's nice to know that equal sums are diagonally related to each other. 11 and 12. Looks like there are 6 outcomes whose sum is greater than 9. Notice I didn't include 9 because the probability said greater than 9 as opposed to greater than or equal to. 6 of those sums were greater than 9, so once again, 6 out of 36 reduces to 1/6. All right, D, sum less than or equal to 6. In this case, it's a little bit different than C, which just said greater than as opposed to greater than or equal to. So in this one, we need a sum that is less than or equal to 6. Well, what numbers are less than or equal to 6? 6, 5, 4, 3, 2, 1. Except there are no sums of 1 because the smallest sum is 2. The sums that are less than or equal to 6 are 6, 5, 4, 3, and 2. And if you count all of them, there are 15 numbers circled. Making sure? Yep, there are 15 numbers circled. The probability the sum is less than or equal to 6 is 15 out of 36. That can be reduced by 3. 15 divided by 3 is 5. 36 divided by 3 is 12. The probability is 5/12. For E, what is the probability there is a 6 on one die or on both dice? Now we're not looking at the sums. We're looking at the individual dice themselves. And we're looking for the probability that we get a 6 on one or both of them. So let's go back to our table, clear this mess, and find all of the outcomes where there is a 6 on one or both die. It's actually pretty easy to do. All of them in this last column have a 6, because that's where the first die was 6. All of them in the last row have a 6, because that's where the second die is 6. Don't count 6, 6 twice. It is a single outcome. It just happens to belong to both the 6th column and the 6th row. If you count, there are 11 pairs circled, which means the probability of rolling a pair of dice and having a 6 on one die or both dice is 11 out of 36. 11 is a prime number, so the only number it can reduce by is 11, but 36 is not reducible by 11. So that's our final probability. F, the probability that the sum is even. I'm going to bet that it's 1/2. My intuition says half the time the sum will be even, half the time the sum will be odd. I may be wrong, but it's always nice to try to get an intuitive feel and see if your intuition was correct. All right, so let's clear out all these. And let's find all the sums that are, I believe it was even, wasn't it? Yes, the sums that are even. Now, if I'd actually accidentally found the probability that the sum was odd, that's the complement of the sum being even, so we could have just subtracted that answer from 1. But the probability that the sum is even, let's find all the sums that are even. Well, 2 is even, 4 is even, so here's all the 4s. 6 is even, so here's all the 6s. 8 is even, here's all the 8s. 10 is even. and 12 is even. And that is 18 of them, which makes sense now because if you look at each column has 3 even sums and 3 odd sums. So if each column has half even sums, then the whole table has half even sums. But from a strictly theoretical perspective, 18 of the sums are even, which means the probability that the sum is even is 18 out of 36, and that reduces all the way down to 1/2. You might reduce it to something different, like if I reduce it by 9, I would get 2/4. But if you're going to reduce, don't stop until there's no reducing left. All right, prime number on both dice. Ooh, might help to remind ourselves what the prime numbers are. The prime numbers are numbers that can only be divided by 1 in themselves. Specifically, a prime number is a number that has exactly 2 factors, 1 in itself. 1 is not considered prime, but 2, 3, and 5 are considered prime. We want to know the probability that we get a prime number on both dice, meaning that we want 2s, 3s, and 5s only. Let's find them. Let's erase all this. All right. We are looking for the pairs where there's a prime number on both dice. So the first die can only be 2, 3, or 5, and the second die can only be 2, 3, or 5. Now be careful, we can't just add up each row and column. For example, I don't want this one even though 2 is prime. Why? Because 4 isn't, and the question was, what's the probability there's a prime number on both dice? At least I'm 99% sure that's what it was, but my short-term memory gets worse the older I get. Yes, prime number on both dice. All right, so basically we need the intersections of all these rows and columns. Going down the second column, come on, draw. This outcome, and this outcome have prime numbers on both dice. Going down the third column, this one, and this one. And going down the fifth column, this one, and this one, and this one. Those are the only pairs of numbers, the only outcomes where both numbers in the pair are prime. It's a total of 9, which means our probability is 9 out of 36, which, as we saw before, actually we didn't, but that reduces to 1/4. I was confusing it with the first one. 4 out of 36 reduces to 1/9. 9 out of 36 reduces to 1/4. And then finally, the probability that the sum is less than 13. This one's actually pretty easy. Why? Well, first, let's clear out all this. Which of these sums are less than 13? All of them. The greatest sum you can get rolling a pair of dice is 12. Every other sum is less than that. So all of them have a sum less than 13, which means all 36 outcomes out of 36 have a sum less than 13. That probability is 1, but that shouldn't surprise you. Why? Because if an event has a probability of 1, it is a certain or sure event, meaning it must happen. And when you roll a pair of dice, the sum must be less than 13. What if it said the sum was greater than 13? That's impossible, and its probability would be 0.